Hello everybody, my name is Jonas Vermeulen. I'm running technical sales for the Nokia Web Scale unit. That's basically a unit that addresses all the hosters, the IXPs, and we basically help them defining what they can do with the network, how to grow the capacities, whether it's on an IP or WDM basis. I'm actually impressed already to see this many people after a likely shorter night. And it's also a pleasure to meet some of the customers here after a long period of COVID, amongst which we have here our Team Blue guys, who were, where are they? They're there, fantastic, who deployed already one of those 400 gig routers last year. And in this session, I will be giving some more hints on what such a 400 gig capable router is all about, what kind of design considerations we had to take as a router supplier, as a router manufacturer, but also give you some hints in terms of how you can select such a 400 gig IP and PLS router. Now, I already mentioned COVID, and obviously that has brought us to the attention to the realization that capacity is increasing in our networks, and that is obviously funneling the drive or the increase in our networks of traffic. Now, as you're looking at 400 gig, of course, that's going to give you more capacity, but at the same time, you should likely still consider the fact that, hey, security is also an important aspect. DDoS attacks are increasing, and that means that on your peering routers, your ingress routers, you will have to still mitigate, you will still have to make sure you can address or you can stop any potential attack. And part of your consideration might also just be power related, and that's kind of what goes into the sustainability bucket. Because what we see is more and more that customers, operators, make that a key decision criteria as and when they're upgrading the networks. It's not like you can always increase your power feeds to your routers. It's not like your data center always has additional power available in the racks. So part of it is also, hey, how can we ensure that higher capacity routers don't drain your power too much, or that they're actually more and more power efficient as compared to the bigger routers as we used to have them. Now, luckily yesterday there was already a few talks about 400 gig. I mean, you've seen now this chart a few times already, that indeed the number of 400 gig pluggables that are being sold is increasing drastically. We're now here 2022, and you see already a very wide variety of pluggable optics that is finding mainstream, and that's all about both multi-mode variants, single mode variants. Single mode variants are the ones that are more popular, also more used nowadays. And you see also there a mix with 2x200, 2x100, which is also used to provide them a fan out for pluggables that if you still want to use normal SFPDD as a breakout. Now this is the chart for 400 gig, and it's indeed like the title already said, the introduction. For us, it's also a matter of giving you some hints about what 800 gig is going to be all about, right? So, and we'll go to basically in that in a few slides from now. Now let's look a little bit more on the technical side. What does that mean now, actually building out a 400 gig capable router? And if we simplify more or less the design of a line card, you more or less see a number of building blocks, a number of key parts that are important as you're scaling out or as you're using such a device. On the left, you basically see just a pluggable. I mean, this is what you obviously see that you need to plug in all your cages, and that's where you have the choice of FR, LR, DR, and so on and so forth. That's going to give you a certain capability to cover a distance. It's also going to give you a certain density on the faceplate. I mean, depending on the form factor you choose. And in the end, that's also you need to make sure that it's compatible with the other device. That basically sits in a cage, and that cage is then connected with a SerDes link towards your router ASIC. And it's that router ASIC that you could say these are the crown jewels of your router. That could be a commodity ASIC, that could be a vendor-specific ASIC, and each one of us has basically a different approach of doing that. What you see here is basically a Nokia approach where we've split up a Mac ASIC different from a packet processor ASIC. I'll come back a bit why we do that, but it's basically ensuring that we get you flexibility, compatibility between different versions of router hardware. And the packet processor is obviously the part where you do a packet lookup, do your MPLS label lookups, one label lookup at a time, multiple label lookups at a time, and so on and so forth, where you have buffering and as well. Now, as the power increases of each one of those ASICs and the pluggables, it's still necessary to cool that. So on top of each one, you will see a heatsink, and you will have a massive airflow that you will have to manage within your router hardware to keep all those components cooled. Now zooming in on each part a little bit. So let's start a bit with the pluggable optics and the cage types. And what you actually see on the cages is that they become more and more universal. And you see that basically two form types more or less remain in that. On the one hand, you have the QSFP, the types that are supporting 100 gig plus type of optics. And the size of a QSFP basically allows you to support 100 gig QSFP28, 200 gig QSFP28DD, QSFP56, the 400 gig QSFPDD, but also it's the same type that is being standardized for 800 gig QSFPDD 800. And that means that if you're now looking for a router and you see those plugs, that you're basically going to have the flexibility to choose to use that port for 100 gig all the way up to 800 gig, or even do a breakout there. We see a same trend towards a universal cage and the 100 gig minus, and that means that an SFP is now becoming available SFP, SFP plus, SFP28, 56, and also SFPDD. It's a newer type SFPDD, but it really is going to allow us to compress or reduce the amount of footprint needed for 100 gig plugs, right? And I'll show you a picture of that later. Now, physically, you also see that on the line itself, quite important is the evolution towards 100 gig lambda as a physical modulation method, allowing basically a single wave or a single optical channel to transport 100 gig. And that is effectively used all the way already in 100 gig plugs, but it's also the underlying technology in 400 gig and 800 gig. And the second part is around everything around ZR, basically allowing coherent technology to be integrated, built within a transceiver in the form factor of a QSFP. And there you see then the evolution where routers become more capable, or more or less take up a role also in the whole transponder networks, because it allows you to do IP over DWDM designs, which in a way is very good for point-to-point designs, maybe to a certain limited extent metro designs, and only for long haul, I mean, only you will have basically a choice in metro or long haul designs to still use more of a traditional transponder design. Now, this slide gives you a bit of an overview what is 800 gig QSFPDD all about. So it's basically the MSA, this is the service agreement to standardize the plug itself that got ratified or standardized last year. And that one, you can already see in the picture, it allows you to use a very similar form factor for 800 gig plugs as compared to what you see now in 400 gig. And then on the faceplate, it's basically going to have the same size as a 100 gig plug. Quite different from 400 gig and lower speeds is the move towards 100 gig SerDes as an interface towards your ASICs and the backend, right? And that's going to be giving an important consequence on how internally your routers have to be designed. Because all of a sudden, your PCBs and your whole boards need to go for an upgraded signaling speed and ensuring that it can transport 100 gig SerDes as an electrical standard to communicate between ASICs and communicate with those plugs. On the right-hand corner, you see there the pluggable modules that will be first on market. I mean, they're more or less the shorter distance ones. And they're also plugs that allow you to do a breakout, right? Because initially, the clear channel 800 gig is not, I mean, that's still being standardized. So the very first plugs, they will be having the form factor of an 800 gig, but will effectively be used as 8 by 100 gig or 2 by 400 gig. And the last bit around form factor is obviously is quite an important one, which is around that power saving aspect. Because as things become smaller, you're actually ensuring that also power can be optimized. And so many times, or what you could consider is rather than using 2 times 400 gig plugs, is to just use a single 800 gig plug, maybe do a breakout, but that's actually going to save you a significant amount of power on the plug itself. To give you a comparison, a DR4 plug 400 gig will consume around 12 watts. A DR8 plug will consume more or less 16, 17 watts. Right? So, and that's basically where we come from. For a slightly bigger amount of power, let's say, how much is it? 25, 30% more power. You're actually doubling the speed, what you can get out of a port. The other plug I was mentioning is the evolution towards SFPDD, where even up to signals of up to 100 gig, you will have basically the option to use either QSFP28 or to use an SFPDD cage. And the clear advantage is that with SFPDD, you're obviously, it has the size of a normal SFP+, so you're going to get a lot many ports on the very same faceplate compared to a QSFP28. And that's how we also see the transition from, let's say, your current form factors of 48 times 10 gig plus, let's say, 6 times 100 gig. You're actually going to be seeing completely another form factor with 48 SFPDDs as an example, plus 6 QSFPDD, which is what you can all put on a 1RU faceplate itself. SFPDD itself technically uses a single. I mean, why can you actually make that plug smaller? It's all to do with the fact that you're not going to use 4 lasers anymore and mix them all together on top of a line. It's actually only 1 laser will be there, and you're going to modulate your 100 gig signal using a single lambda, so a single optical modulated signal to get across from A to B. From a distance perspective, you see the regular form factors, so you have SR, DR, FR, LR as well there. I said, like, how do you then effectively use 800 gig? One of those models is obviously connect them back to back, 800 gig. The reality is that you won't always have a lot of 800 gig routers around or 400 gig routers around, so you can obviously do a breakout. How do you do such a breakout? Well, it's pretty like what you do today. You basically either use a splitter cable or you use a certain optical patch panel or a breakout cassette, so that you have an MPO cable coming from your router. You link that to a cassette or to a module. From where onwards, you nicely have like your 8 or LC connected fibers towards an 100 gig DR on the other side, as an example. Or to do the same with FR, if you do 2 times 400, then you basically split your MPO cable into LC cables, 2 LC fibers to the other end. Every time what you see there is indeed, again, the use of 100 gig single lambda. Basically, again, 100 gig modulated signal to transport your 100 gig traffic. Now, last bit, a bit around the plug itself. So the transceiver itself, you see a schematic view of what is all on here. And if you look from left to right, you basically see on the left-hand side the photonic driver, which is basically your pump or the place where your laser is. It converts your electrical signal into the photonic or into a light-switched signal. And that's where you also need your 100 gig signal lambda. That's where it all comes into and what is being standardized already. The grunt or the real work is being done on the DSP side. That's where all your FAC is done. That's where all your modulation is being calculated. And that's also the place where most of the power is being consumed. And then on the right-hand side is your attachment unit interface. And that's basically that attachment on your PCB that ensures that you're getting like your 100, your 400, or your 800 gig traffic from like your router ASIC itself. What is important here is that on 800 gig, it's moving on to a 100 gig SerDes interface, right? IEEE is standardizing. You see the number there. You can look that up. But that's, as I said, is a quite significant step up from the way how 400 gig transceivers are realized, because that's only using 50 gig. Now, what is SerDes now? I mean, as I said, there's a connection between your ASIC and a cage. And you see that from, as technology evolves, you basically see there 10 gig moving on to 28, 56 gig. Now basically 100 gig. And if you then look at the line, it's effectively using now also PAM4 on your electrical signal. So it's not anymore just a black and white signal. It's actually a PAM4, which in a way is increasing complexity on both ends. But at the other side, it's, well, reducing symbol rate. So you're still keeping your 56 gig of symbol rate. But yeah, that additional complexity will allow us to have higher I/O and will allow us to support those higher speed pluggables as well. Now, why is that important also, that 100 gig SerDes? Is because that needs to link up to your router ASIC. And as I said, that router ASIC then needs to work on 100 gig SerDes. You have then there the option as a vendor to bundle that all in one big chipset. I mean, some certain Broadcom chipsets do that as well. What we as Nokia have done with our own silicon is to separate out what we call the MAC chipset, which is your media access chipset. It's basically where your front end, your media speeds are defined and where they are supported, and your packet processing chipset. On the MAC chipset, why do we do that split? Is because it allows us to create much more flexibility and evolve faster in supporting new speeds, to create flexibility there, to do more things that are only related with like your interface itself. So what do we do there as an example? We allow for intelligent aggregation, which is a way for us to do pre-buffering, to catch like microbursts and so on. I mean, they have nothing to do with like your packet processing, so it's kind of nice if that is split off. We do a certain level of QS processing there already. Things like FlexE or MACsec can also be implemented there. I don't know if FlexE is a common term, I mean, but it's basically a way for combining multiple, let's say, optical or 100 gigs that you have on the line into a logical higher speed interface in your router. So that means that if you were to configure a 4 or an 800 or even for us a 1.6 tera logical IP link, that down on the line it could be realized as up to 16 individual 100 gig links. And that could be useful if you're, as an example, your transponder or your optical network doesn't quite support the higher speeds yet. At least you can realize them with lower speed links. On the right-hand side, what is important as well, if you're choosing routers, is how you want to have your memory implemented, right? On that packet processor ASIC, the biggest chunk is memory there. That memory is used for QoS, but is also used for any kind of memory lookup. That could be FIP lookups, that could be ACL lookups, that could be label table lookups. And you want to make sure that it can all happen in a single pass. I mean, the worst thing is that indeed you need to do packet recirculation because you can't look up enough labels at a time, or that you can't process enough ACLs at a time, and your peering router, maybe you have 1,000, maybe 100,000 ACLs, and then you have to recycle your traffic, right? And that would cause delay in your forwarding. So important is the quality and the speed of your memory that you have on board of such a router ASIC. Now, I said cooling, I mean, and we come there to the last part here. Cooling, in a way, those line cards, every part consumes more power. So how can you deal with that increase of power and heat production? On single appliance system, I mean, there is only so much you can do. You just have to have a lot of air going from front to back. On chassis-based systems, basically the evolution has taken place to go from a mid-plane or a backplane design to basically have an optical cross-connect design so that air can flow faster and better through it, and that each component can individually be cooled. Again, on power, what is another method of making sure your line cards can be cooled? I mean, part of it, why do we have to do something special there? I think what you see is that as the evolution of pluggables goes forward and higher speeds are basically standardized and brought to market, you see that the individual power is just going nicely going up. And I mean, you see a bit of a trend line, but there is basically no way going back. I mean, 100 gig was, QSFP28 100 gig was quite low here, was nice. But now here we're looking at 400, 800 gig, reaching values above 15 watt, over 20 watt. If we think about 800 gig coherent, we're even looking at 26 watts, right? What do you need to do on the line card for doing that? I said you need to push a lot of air to cool that, but part of it can also be just an engineering solution with, rather than having pluggables stacked above each other, to basically build them on each side of the PCB and making sure you can basically have heat sinks that go right on top and below your transceiver pluggables itself. And that's also, if you look at the top, that's kind of your most straightforward way. It's a stacked SFP cages. That's what you see on most appliance systems, most commodity switches as well. But what we believe is that if you want to enable 400 or 800 gig on all your ports of your switch or your router, then you need to go basically with an approach where you do what we call a belly-to-belly SFP cage design, right? And we see that in certain examples. I mean, otherwise there is no other way you can have ZR optics or even the 800 gig variants across all the ports in your router. So with that, I'm basically come to the conclusion of this session. Basically, what I've explained to you here is a number of design considerations, a number of things that you can keep in mind around when you select a platform. A few things around platform, mechanical design, power, cooling. Give you a few hints around what is important around data plane and chipset design as well, and give you some further detail on the optical transceivers that you could use to support higher speeds. And with that, I thank you for your time and attention, and open the floor for questions.
Let's see, who's first? Hi, Rory from Google. In a few slides ago, you had a graph of up and to the right of power budgets. So
This one?
yes.
Yeah.
Doesn't that imply like increased demand for cooling? Do you see
It
a
does.
point where we have a problem with cooling and can't move forward?
It's going to be an interesting challenge, both for us and for the transceiver producers, to ensure indeed we can make somehow a ceiling, or we can indeed define a dip in that. But this is basically what is being standardized at the moment, what we have in view. And yeah, that's more or less what we can design for at the moment. I think it's going to be interesting indeed, because I mean, after 800 gig, we see already certain manufacturers going now to defining 1.6 tera. How that, how the power budget for those transceivers is going to look like. Thanks.
Any other questions?
Yes, thank you. I was wondering about the spike to the left side. What happened there? I'm not in the transceiver game.
That's okay. Basically, it's a bit a small font here on the slide, I suppose. But I mean, this is a CFP cage. So as 100 gig was being standardized, or as technology was evolving and 100 gig came on the market, initially it wasn't possible to trim that down or to compress it in a QSFP form factor. So it had to be the bigger CFP cage, and that by itself just required and demanded more power. The DSPs back then were just not as good as powerful. It needed to just have more power to modulate that 100 gig signal. And that's basically why you see that spike here. Luckily, QSFP28 came around, and we're all enjoying that, 3 or 4 watts that 100 gig needs now.
Do we have any other questions?
Henrik Kramselund from Security. I'm doing a lot of security for enterprise customers, and I think it's all nice and well with 400 and 800 gigs. You forwarding a lot of traffic to enterprise customers. And some of that traffic will be unwanted. Can we expect the feature set and wire speed filtering to be available for these?
It's a nice question also for us. Because our rate, there is a clear difference there between what kind of chipset you have in your router. And we see that also in our own benchmarks. What we design our chipsets for, the Nokia chipsets, is to maintain ACL filtering capabilities at the line speed at the same rate that you can push traffic through, right? So for us, we ensure that we do that single lookup through the chipset to cover our whole ACL scale, right? And for us, that's 256K ACL entries on ingress. So we do make sure that it's actually done at line rate. And whether you do it at 4 or 800 gig, line cards itself, they're going now to around 18 tera per line card. And we actually make sure that is all done properly. And then that covers your ACL capabilities, what you can expect from routers. So it's everything layer 2 to layer 4, and to a certain extent also packet, looking deeper into a packet.